Welcome to Lesson 6, Reaction Rates and Chemical Equilibrium. I'm going to let you know straight up, this is one of the hardest chapters in the entire class. So with good luck, it gets a little easier as we go. But for bad luck, I have to tell you, I think this is actually easier in your more advanced classes, like in college. And here's why I say so. This particular chapter tries to bring in three pretty big ideas: reaction rates, chemical equilibrium, solubility equilibrium. And then many times in an AP class or a college class, they break it into 3 chapters. And the extra information actually makes it easier in my thoughts. But remember that when you get stuck, if you're writing down all your formulas, showing your work, using handwritten notes and not just copying things off the internet or looking at the screen and feeling like you got it, you'll do better. So handwrite your work. But I'm always here for you. Email me anytime. I actually love this chapter. The equilibrium topic for this chapter is my favorite. Equilibrium is really useful. But let's start with reaction rates. I've got a steel block, and I've got my kitchen tongs. Don't try this at home without a responsible adult. Okay, but I'm going to burn this steel, right? No. But now I'm going to take a little bit of this steel wool and try burning it. Woo! Pretty hot. Don't do that at home. Why did that steel burn and the others didn't? Reaction rates will tell you. Another thing to think about with reaction rates is kind of thinking about what are the molecules doing. And you've got these things called activated complexes. So there's a picture in the book, and this might be helpful, but I like to think about activated complexes as particles that don't actually exist because they're in transition. So here's my little octopus. He's inside out. That could be the reactants. Now I'm going to add enough energy, the activation energy, so that my reaction can happen, and so I can use this as a model. Here I am in the middle. Nothing really exists now. This is the transition state. The activated complexes are not a particle. But now, here's my product, my octopus. Reaction is done. The octopus exists right side out and inside out, but it's not an octopus while it's in transition. I hope that helps with activated complexes. And then I made one more thing for you. When you get to the second part of the chapter and you're thinking about equilibrium expressions, you're going to see these K's, and the K's are actually your friend. For one thing, they don't have any units, which is pretty cool. And then if you remember when you were doing concentration and molarity, you put everything in brackets to indicate molarity. So here's molarity again, okay? You're going to find the concentration of the products and divide it by the concentration of the reactants. It's going to give you a ratio, just a number, just a decimal number. And that's your K, which is the equilibrium constant. KEQ is how you could write it if you're saying, hey, I know this is at equilibrium. You could write just Q if you're questioning whether it's equilibrium. You could say Ka. Our next chapter will be acids. You could talk about the equilibrium for acids. You could say KSP, the solubility. Remember our green bottle with the food coloring and the baby oil? How much food coloring is dissolving in the water? That's my KSP. What does K tell you? Well, it's a ratio, right? If you've got a lot of products and not very many reactants, you're going to have a big K. It's just a fraction, right? 4 over 1 is a big fraction. 2,000 over 7, it's a big number, right? 2,000 divided by 7, you're going to get a number bigger than 1. But if the concentration of your products is less than the concentration of your reactants, if you have a lot more reactants than products, then your K, equilibrium constant, is small. right? 7 over 2,000, 7 divided by 2,000, that's 0.000 something, right? It's a small number. So if your K is small, it means at equilibrium, there's a lot of reactants and not a lot of products. Or the reaction didn't really go, right? Reactants yield products. If your K is big, that means you have a lot of products and not a lot of reactants. And your reaction did go. So do you see how if you just know the K of a reaction, you can tell if it's going to work or not? Even before you do it, you could calculate. So let the math be your friend, do your algebra, watch your units, but not with K, because K doesn't have any units. Okay? Good luck. Take your time with this chapter. Bye.